So I'm Tiago Gomes. I'm from the University of Minho in Portugal, and I mainly work with embedded systems, not directly with AI, as you, but anyway, I will try to put my expertise of the embedded systems and try to combine with AI systems. So today I will be talk about how to use machine learning with embedded systems, okay? So from the cloud to the deep edge of the network. The agenda for today, okay? So how can we shift AI from the cloud to the deep edge devices? Someone was asking about this before, okay? So this can be a new trend. We are already doing this, okay? Putting AI on small embedded devices and not only on the cloud, okay? How can we do this? And then I will show our current solution that we call the Decenter framework, which basically supports not only the inference, but also the training on embedded hardware. And then how can we use our framework to tackle the cybersecurity threat? We are at the cybersecurity workshop, so we combine both. That's the question, and then some final remarks to close this presentation. Okay. As Professor Cole said in the beginning, machine learning can be used on several IoT applications. He was showing several examples. Okay, from healthcare, road security, industrial agriculture. I think you use it a lot, right? With agriculture, for the crops, for the everything. But I mean, AI is everywhere. One of the applications that I will talk about is everything okay with this mic? Okay, can you hear me better now? Okay, thank you. So one of the applications that I'll be talking about, I will just focus on the autonomous driving applications. Sandra already talked about mixed criticality systems. How can we deploy safety and security on autonomous driving on vehicles, right? Smart vehicles. And so this will be mainly my my application field that I will talk about, okay? If we think about AI on these kind of applications, okay, we can use the AI on several like tasks, right? Sensor reading, the parking assistant, the collision avoidance, SLAM, these kind of things. So we can collect data from several sensors, process the data, and make decisions, okay? Of course, there are critical decisions that we have to make in real time, like the collision avoidance, the real-time decisions, and others features. Okay, I won't tackle the security part of this. I will just talk about the AI part of making these decisions. If we think about how can AI help in taking these decisions around these applications, okay? If we do this inside the car, as Sandro said, we have the swap-C requirements. Some of these decisions would require powerful hardware, right? Powerful CPUs, a lot of memory, GPUs, these kind of resources. So it's not always possible to do this here. So this will end up with high cost hardware and as well high power consumption, right? And if we are talking about an electric car, this has extra power consumption. Oops. I'm sorry. So one solution to solve this, right, is the centralized learning approach. If we take this example again, okay, so usually the training and the decisions are made in the cloud, right? It's where the hardware is, right? CPUs, GPUs, memory, everything. So usually the car takes the samples from the sensors, okay, sends the data to the cloud. The cloud infers the receiver data with the powerful hardware, and then the data is sent back to the car, and then the car takes the decision. The problem with the cloud is that what if we have several devices sending data to the server, right? So the server has to make decisions to a lot of edge devices. And also, if we rely on the network to do this, right? If the network breaks, and someone was asking about the network before, if the network breaks, or if the connection is not good, or if we have just limited bandwidth, right? The decisions can take time to travel through the network. And this can result in some catastrophic, right? So this is the problem of having a centralized learning, okay? For the edge, it's good because we don't need high hardware resources. It can be easier to deploy, okay? But then there are some issues that we cannot solve, such as the network, okay, the scalability issues if we have so many devices connecting to the cloud. And then we can also talk about the privacy concerns, right? Data is flowing on both ways, okay? So the new trend now is to deploy a decentralized learning solution. So the machine learning is shifting from the cloud to the edge, okay? This can enhance the privacy, can promote better scalability, okay? And then we can adapt the models to the local data, okay? And this can be like faster. When thinking about faster is that we don't have to have information flowing through the network. So it can be more deterministic, and we can say like it's more real-time system, okay? And the problem is, okay, we need the hardware to do this locally. So the question now is how to enable both the inference and the training in the edge devices. The first challenge is, as I said, as Sandro said as well, the hardware has limited resources. So usually, and if we think about ECUs or devices with MCUs, okay, usually the hardware is like limited, right? We have single core processing units. They work at the low frequencies, okay? And this is the major problem, is the memory, okay? Usually the memory is not, is a resource in terms of RAM and flash that is limited to some hundred of kbytes, okay? So it makes unfeasible to deploy large models, large data. So this is the first challenge. And then this is the main challenge, is the inference process and the training process. Talking about the inference process, some hardware manufacturers, okay, such as ARM, and now with the RISC-V, they already provide some software libraries for the inference process. ARM uses the CMC-ZNN. I don't know if you are familiar with this. And RISC-V now recently, there's the PulpNN solution. So we can make the inference on the edge. We don't have to send data to the cloud and wait for the reply. And then now the training process, okay? Now we can also do the training process in the edge. The main challenge here is optimization step, okay? Because classical methods, the methods that we know, to the edge or to the embedded devices, they cannot fit really the low edge devices, okay? Devices that mainly are composed of MCUs with limited memory and hardware. Thinking about the state of the art of these optimizers, we have mainly four: the GD, SGD, ADAGRAD, and ADAM, okay? But because of this of this limitation, okay, ADA and ADAM, they have high computational costs, so they cannot be offloaded to the microcontrollers. Mainly they run on APUs, not MCUs. About the GD, okay, this has a high memory footprint. So if you want to deploy this, it can actually, it has low computational cost, but high memory footprint. So it's not suitable as well for the embedded devices. Talking about the SGD, okay, it has the best trade-off between the computational costs and the memory footprint, but it can be considered slow to run on embedded devices. Okay, and there's no MCU support at all. That's the problem of these optimizers. So what we have been doing and working with this, because we are from the embedded systems group, we work with embedded systems. So the challenge is always how to put complex things on low-cost MCUs. So back in 2022, we came out with this lightweight version of the SGD. So we took the SGD, okay, and we optimized it to run on low-cost embedded systems. The optimizations that we did, okay, we end up with a low computational cost, low memory footprint, okay. We improved the latency a little bit, not as much as we wanted, but we now can run on MCUs, okay. So this is the major contribution. We can now support MCUs, something that it could not be done in the past, okay. And then we gave support to the float and the quantized implementations of this optimizer, okay. The only thing is that we only tested with one MCU, which was an ARM Cortex-M3 from STM, okay. It supports floating point unit and DSP accelerator, so we could somehow improve this SGD algorithm. So this was when we proposed the LSGD. And then last year, we we improved this algorithm again, okay, to support not only one architecture, but more than just one architecture. So we start from the ARM Cortex-M7, which has the FPU, DSP, instruction, and data cache, and then we also implemented this LSGD algorithm on ARM Cortex-M4, okay? That also has FPU and DSP. And then to extremely low resources, such as the ARM Cortex-M0, okay? But this time with no FPU and the DSP. So basically the contribution now with this paper, which was the Centre, the decentralized learning and inference, was we support more MCUs, and then we just test the trade-offs of having different components inside the architecture and see if we can still train the network and make the inference. And now, recently, we just gave support to more architectures. So we call it the Centre V. It's something that we finished recently, okay? It's the first of its kind, so it's the first support for the RISC-V architecture, okay? So it's the first porting of LSGD to RISC-V, and we also support the float and the quantized training, okay? So at the moment, we have this framework that we call the Centre. It will become public very soon. We are just finalizing some parts. We want to make this open to the public, so you can use the training and the inference at the deep edge, okay, with this framework, supporting different classes of MCUs with the float and the quantized training support. So just to wrap up, okay, there are differences between these architectures from the Cortex-M0, which is the most constrained architecture, to the M7, okay? So We give support to the quantization in all of them, but we just give support to the FPU where this component is available on the architecture. Just to show you how this actually works, okay, some empirical evidence. We tried the LSGD on 2 different architectures, okay. The STM F767 from STM, okay, running at 216 megahertz, okay, with FPU support, and then the gap Minho running at the same clock frequency, okay, with RISC-V core without FPU. All these boards are microcontroller boards, okay, don't forget that. This is just tiny, very tiny processors, just composed with microcontrollers and some sensors. Of course, these are the dev kits, we don't have sensors, but there are several components inside the car that actually use this kind of architectures. So that's why we took this as an example. Okay, for the software, we just run 2 different models. One is the CogDist. I don't know if you know about it. Okay, it's a benchmark that is used to detect the distraction in drivers, like the fatigue and everything. So you take the wheel, steering wheel, while you're driving, you have sensors taking data from you, and they can see if you are sleeping, the blink rate, the breathing rate, the heart rate, if it's daytime or not, and depending on the features that you have on the car, it can then classify your behavior, your status as you are tired or not. Basically, this is what it does. And then the second one is a benchmark on preference when you buy in your car. This is just to try 2 different models on the hardware that can somehow represent the behavior of having a machine learning model on this kind of devices. Okay. Here we have more outputs, but this is not really important for testing the performance of the model and the algorithm itself on this kind of hardware. So comparing using the baseline, comparing the SGD with LSGD, and this one was not supported by microcontrollers. This one, we gave support to microcontrollers. And what we can see is that for the performance of the algorithm, we didn't see much accuracy loss, just 1.3%. But with the LSGD, as expected, we improved the processing time. So the execution performance was improved without losing any performance on the algorithm, on average. Okay. But the major thing was we could improve the SGD so much that the memory footprint was only 9.4% of the original algorithm. And we did this for both models, okay? So both models gave actually good results. And then we compared the quantized version of LSGD versus the FPU support of this model. And again, we end up having almost the same results. In terms of the algorithms, performance, it didn't change much, okay? Accuracy was almost the same, okay? And then again, we got a reduced memory footprint. 60% of the LSGD float 32 version memory footprint, and again, we improved the execution performance. I will show you some results in terms of milliseconds, so you can see how fast this can be and how this actually can be used on a real-time system or a real-time decision-taking system. Okay, then comparing on the 3 versions of the microcontrollers that we use, the architectures. Again, I don't know if you can see it from there, but we can see that, again, the performance of the algorithm didn't change much, okay? Precision, the recall, F1 score, the accuracy, they kept the same, almost, okay? This for the M7, this for the M4, and this for the M0, okay? The M0, because it doesn't have the FPU, if we use floats, the performance, the execution will be affected a lot, okay? So that's why we don't use the FPU, the floating approach on this one. But again, this is just to show that the performance of the algorithm keeps the same as the original SGD version, okay? So the conclusion here is that even using different MCU classes, the performance doesn't impact, which is good. Now, in terms of memory footprint, okay, and the execution cycles, for the execution cycles, higher is better. For the memory, lower is better. So we can reduce a lot the memory, okay, while improving the execution. Why? If we use DSP and FPUs from this platform, the performance can increase a lot, okay? Also, in this platform, we have data and instruction cache, which helps increasing the performance as well. Okay. Now comparing the LSGD with in the RISC-V platform, okay, we can achieve the same kind of results. Okay, the performance of the model, it doesn't change. This is the main takeaway we can take from here. Now, something that I want to show is the execution performance. Okay, so improving 1.7 times, 1.8 times the original algorithm, it doesn't actually show how much we improved. Okay, what we can see from here is that now we can take only around 30 milliseconds, 20 milliseconds to execute the inference step, which is really good. So we can do it, we can make a decision in less than 30 milliseconds, which is really good. This can be much faster than sending data to the cloud, wait for the decision, and then receive the data, and then we take the action. Okay, and we are doing this with MCUs. Okay, that's the major thing. Okay, again, the float against the integer version of these two models. Okay, it didn't change much. Again, the performance of the algorithm. Okay, it just affects the execution. Again, the execution. Using the RISC-V platform, the execution can be even lower than with ARM-based platform. Okay. Of course, this depends on the hardware and, of course, the library that we are using. With RISC-V, we use the PulpNN, okay, which results in slight different results if we compare with the other libraries. But again, this is really good. Okay, this is having these results opens doors to using other models on this same hardware. Okay, some takeaways from these previous slides. Okay, using AI in the edge, it's possible. In the deep edge, it's also possible. So we can use now MCUs to train the network and to make decisions locally. So this keeps data local. We don't have data flowing through the network. I think this solves a little bit of these privacy concerns, right? I think it can help a little bit with this kind of cybersecurity issues that we are having now. So the data keeps local. Also, it reduces the network pressure. When we have a lot of devices, connected devices inside the car, if all of them needs to communicate, and if the network is not available, or if we have a lot of data to transmit or to receive, this is also not good for the critical decisions. So doing this locally, it helps mitigating the network problems. And then, of course, we can improve the overall execution performance because we don't send data to the network, we improve the processing time. If we combine this improvement, okay, we get those 17 to 30 milliseconds taking a decision for the model. But now, how can we link this to the cybersecurity, right? I'm from the embedded systems. I work with embedded systems. For me, AI models are just applications. Just to be honest, we just run firmware. We just run applications, binaries. But can we combine this? Can we use this approach of running ML on edge and somehow link it to the cybersecurity side? Well, I think so. Now taking again these autonomous applications or smart cars example, okay? The traditional systems, they, as Sandro said before, they have isolated ECUs. That was before. And isolated means a lot of ECUs not communicating with each other or just communicating inside the car, not with outside network. But now, of course, we have always on vehicles, right? They need connectivity for everything. They use connectivity for everything. Okay, LTE, 5G, Wi-Fi, Bluetooth, so we can open the doors, the car. We have Wi-Fi. We have also other technologies for vehicle-to-vehicle communication. Okay, now everything is connected. We can also put the smartphone, right? Install applications, these kind of things. And now we can run AI at the edge. If you use our framework or other solutions just like ours, you can actually run AI in the deep edge, on the microcontroller side, on the small ECUs, right? More problems, updates over the air, right? Again, you need connection. You need important firmware to come from the cloud and then to be installed on your smart vehicle. This can be also a problem. So this opens so many attack vectors that you will see on the next slide, which means that from the network to the car, there are security breaches, and then also from the car to the network. Something that was not a concern in the past, right? You have your car, you open your doors, there's no connection. If you want to break your car, break in your car, it has to be physically. You need physical access to break into your car. But that was in the past, right? Now, modern cars can be hacked. Okay, this is just an example. Back in 2022, there was a problem with the Tesla on the BLE. So basically, you can open your car with a BLE. I don't know if you have a Tesla. I don't have. I still have these kind of cars, okay, not modern cars. But there was a problem. I don't know exactly how they did it, but basically the attacker could use the Bluetooth to open the car. This was a problem. And this attack didn't come from the from the network. Just by having physical access to the car, you could open the car. Okay, so the car, when the phone was nearby, it could unlock the doors and enable the driving mode. Okay, so basically a thief could enter and drive away without being the owner of the car, the real owner of the car. This was one example of attacking, of a security breach of a car. Example number 2 was with the Range Rover attack. This was back in 2023, where you could have access to the CAN bus via the headlight wiring, and then you could inject fake lock-unlock signals to the ECU. So you could open the car, basically. So you wouldn't need your key to open the car, but just by injecting fake unlock and start signals, you could actually open and start the car. And then at the end, you will have full vehicle control and no alarms would be triggered. So again, these kind of attacks came from the physical access to the car. Just by having access to the wires of the headlight, you could actually send signals to the car. This is also a security breach. And there are so many, okay? There are so many attack vectors that you can use to take control of the car, or at least to do something that you don't want to the car. Just like access the infotainment system, the telematics, wireless fobs, they are everywhere, right? We don't actually need the key to open the car. They are inside our pockets, or use the mobile phone, and when you are close to the vehicle, you could actually enter the car. But again, this is a major issue, a major attack vector of this kind of modern vehicles. Also firmware updates, and then other kinds of attacks. E-call center attack, so you could call the call center and make also give some fake information, and then you can have access to other parts of the car. So in conclusion, modern IoT connected cars, or the devices inside the car, specific devices, are still vulnerable. There are a lot of solutions that you can use to mitigate these problems. Maybe isolation, as Sandro said, using hypervisors, right? These kind of things can help, but still there's a lot of vulnerabilities that can be explored to access the car. So, and then I was thinking, okay, I know how to shift ML to the edge. Now I know there are a lot of attacks that can be used to the cars. How can we combine these two things and maybe have a solution that can help mitigating these attacks, okay? Because the attacks can come from the network, okay? For example, updates over the air, remote code execution, okay, command injections, these kind of things can come from the network. So this is a problem, right? We need to protect this side. But from the examples from the previous slides, we can also see that physical access to the car can also inject or provide attacks, device to network attacks. How? Data poisoning, spoof of telemetry. I remember now about other attacks that use fake. Some cars have LiDAR sensors, right? You know LiDAR? Yeah, they have LiDAR sensors. And there was an attack that the attackers, they put the LiDARs on the road and they can send fake signals to the car. So you can spoof data of the other system that the car would think that there's a stop sign ahead, or a traffic light ahead, or someone crossing the road. So the car would just brake just to avoid the collision. These kind of attacks have been explored, and they actually work. Okay, there are a lot of things that you cannot actually do to against these kind of attacks. Okay, and then also if you have the even if you have the network running, okay, inside the car, you can also send fake data or malicious training data to the model. So at the end, the decisions won't be as good as they should be. Okay. So again, we have attacks on both ways, or we have problems on both both ways. So the threats flow both ways, from the cloud to the edge, and then now from the edge to the cloud. How can we solve this? Okay, if you think about our solution, the Decenter, one possible solution, we didn't implement this yet, this is on the next steps, but now I'm thinking about having someone working on this, deeply working on this. So what about if we, instead of running the models that we were running so far, we could run, again, network. So we can use the federated learning approach to have one network attacking the other network, so the other network can learn from these attacks. This would help in validating local sensors data before it's used by the other AI models. And also, this could help on so much other things like device anomaly detection and so far. This would be running right on inside the car. It's local AI models. Second approach, of course, the communication layers. Right, we need to protect the communications. Not only encrypting data is not sufficient. We need to do something else. So something that I was thinking about, why not using some kind of IDS system, lightweight IDS system that can also run locally on the car, that would protect not only the communications from the outside, right, but also the communications inside the car. So even if you attack the CAN bus or the network bus, there will be something helping in monitoring the network and protecting the physical or local attacks to the networks. This would help, of course, or provide defense in both directions, right? From the cloud to the edge, and from the edge to the cloud. This is just a proposal. I think this could help solving the problems that we have seen so far. So taking this, okay, the Decenter framework, I think it could be a good approach to do the things that I've said before. Okay, so I think I will put some students working on this, right? Design an IDS to the local network and then integrate the IDS to the Decenter framework. So we could test this on real cars, right? We have so many projects with Bosch car factory in Braga. They basically in Portugal, they basically build systems for the automotive sector. So I think we could test this and try this with them. So basically, yeah, as I said, taking the things that we have done so far, because now you can use the machine learning at the deep edge, so why not using this inside the cars to protect the network by implementing IDS or other kind of systems. Oh, sorry. So, as a final remarks, okay, from this talk, you can see that using ML at the edge, it's possible, okay. With our framework, we can actually tackle the tiniest IoT device, okay, with memory, constraints, the CPU constraints, FPU constraints, and basically we can tackle any class of MCUs. Well, we actually have been using this, but not within this context of the cybersecurity. So we know cybersecurity is critical. The connected vehicles, they have their own flaws and attack vectors. So why not combining this to tackle the cybersecurity as well? How? Building an AI-based IDS system so that it can also run inside the car. So what we want to do now is to promote our framework and use it against these problems. And, well, this is the end of the presentation. So if you have questions, just...
Thank you very much. Okay, I will open the floor to Q&A.
Hello, I'm Suhas from Android. So you showed us the benchmarking of your algorithm, right? Since there are almost 40 or 50 billion IoT live in the world, and they generate like multi-billions data each day. So I was wondering about the flash and RAM memory you have used.
I can go back some slides if you want.
Along with the DNN architecture, if you can show us or share your experience, the architecture of neural network you have used. And my last question was, for on-device training, you use numeric data, right? But in IoT, maybe we can have audio data from microphone and small size images. So can you do training on those data as well?
Okay, thanks for the questions. We have used this class of devices because they, in our opinion, they are good, they can represent real ECUs based on microcontrollers. So these kind of sensors, they basically, as you said, they use like the numeric data for the tasks they are doing or performing, right? So if you have like a pressure sensor or some kind of the proximity sensor, they mainly use like the numeric data, and they mainly use this class of devices. So in terms of the performance of the algorithm, as we saw, it's the same, almost the same for every device. No matter if you change the class of device, we will have basically the same results for the performance of the algorithm. For the execution, yeah, it may change. So when you choose your target device, you must take this into account. If it's just a temperature sensor, you can use like a small device. But if you need more resources, you have to adapt. But still, the algorithm will perform the same. The execution will change. This is for the first part of the question. The second part of the question was, I'm sorry, I forgot already.
So last question was for on-device training.
Okay.
So can we train for audio and small size images?
Again, it depends on the application. We didn't try the audio and video on this class of devices. But if you use an APU, like a Raspberry Pi, they use a processor, application processor, not MCUs. That could be a good example where you can apply audio and video training. Okay.
Yeah. For Raspberry Pi, maybe they
But
are.
for the MCUs, we haven't tried that.
So they are heavyweight and have multiple.
But with a Raspberry Pi or this kind of processors, usually you have more memory, right? You have more. You don't have only one CPU core. You have multi-core. It's a multi-core system where you can actually have more computational power, and you can have 8 gigabytes or maybe 16. I don't know if the last version, if they support already that, but with 8 gigabytes of memory, you can do a lot. If you compare to the 1 megabyte for this MCU, I mean, the orders of magnitude are really different.
Okay, I think I was just wondering about the MCU because I was working on 256 kbs RAM. So I was just wondering if you can do some on-device training for audio and image.
We
So
haven't
that's
tried, but of course, because if you have limited hardware, I wouldn't use an MCU maybe for video training.
Yeah, right. We have power limitations, so for remote, we must
Yeah.
use
I would-
MCUs.
I would adapt. We have ECUs. I mean, we have a lot of, we have some projects with a lot of applications that we do with industry, okay? Most of them use MCUs, and, but, I mean, if you use some ECU to control the pressure, temperature, the proximity, the parking sensors, an MCU, it's enough. Or the steering wheel sensor, because now everything, not everything, but I mean, the projects we have, they target, how do you call it, steer-by-wire sensors. They don't use anymore the physical connection to the wheels. There's a sensor with the steer and then a motor to change the wheels. It's called a steer-by-wire system. Even with that system, we use MCUs, not application processors. So it depends. If you want to train something more powerful, you change from an MCU to the APU.
Okay, thank you.
Thank you for the question.
So it's very interesting works and open up many things to explore, I believe.
Thank you.
But as you mentioned, you have been evaluating the latency and memory consumptions. How about the power consumptions in this framework approach? Because most of the AI or machine learning model trainings and inferencing usually consuming a lot of energy. Right?
That's a good point. We haven't measured the power consumption, but usually MCUs, they have really low power. Yeah, the consumption is really low. So I believe that won't be really an issue since, of course, it depends on what you are running, right? And how many times you run the algorithm. But
Yes.
I mean, if you do something that takes only 30 milliseconds to execute, and it depends, of course, on the frequency you run it, but I mean, I think for an MCU, this is quite okay.
Yeah, yeah.
And we will, at this point, we are not concerned about the power. Of course, it's an important issue, right?
Yeah, it would be nice if we can have the figure of that consumptions.
We don't have yet, but it's something that
Session.
we can put here on the roadmap, for sure. Because if we talk about the swap C and then we don't measure the power,
Sure. Of course.
you are right. But the first challenge was actually taking the latency as low as possible.
Possible.
That was the main challenge. Because before, this kind of algorithms could not run on MCUs. So that's the challenge that we saw first. Okay, why? Okay, the models are too big, so we need memory. It takes too much time to run. Okay, so let's optimize and make it like faster. And then, okay, this is good for ARM Cortex M7. Why not M0? And then we took the M0 to optimize again. That was the challenge at the beginning. And
Yes, sir.
this is what we did. I think it's here. I'm not sure if that was for ARM, but it doesn't matter. Even
Yeah.
with the RISC-V or the ARM MCU, we could achieve the same results, or almost the same results.
Thank you. May I follow up with the other question? May I follow up with the other questions?
Yeah. I
Yeah,
don't know if I have.
Still have time? Yeah, regarding the
And then control the time, sorry.
yes ideas, your view on the
Yeah, this
about
is
the ideas. So as your conclude at the end also, since this is very interesting also, but we know like many developers on the firewalls trying to uh, how to say to tackle as processing time as small as possible. I mean, it's like because we are dealing with the packets.
yes.
So if we process too long, then meanings we are not blocking if there are some vulnerable things or malicious things. Um, since you how to say triggering the ideas why we don't put the firewalls on every car or something like that, right? And what is your view in this applicability?
Okay.
Should we do it in every car, or should we just like splitting? Like my view is like, is it possible to split between a control plane and data plane kind of things, meaning separating the processing
Okay.
that could be combined with the fog computing or something like that, then combining with this edge device computing. Since mostly in many car companies, they have some sort of fog computing environments that connected to every of their cars, something like that.
Okay.
So meanings like to reduce numbers of processing at the edge, but still effective in the just ideas.
No,
But
it's-
I just want to know
This,
your
the-
views on
this
that.
is the, this is a
Thank you.
good point. This is also just an idea, okay? As I said, I mainly work with embedded systems, but I took my master's on telecommunication engineering. So 15 to 20 years ago, I was actually exploring these IDS systems. That time, they, if I remember well, they only work with the static data, static information, okay? And they were complex, and they would require complex systems to run. During my PhD, I just look at this a little bit, and then we just realized that you can actually use like a distributed IDS system on small devices, small IoT devices or edge devices. There was one, Suricata, I think, or Snort, I don't know, that was ported to this kind of devices. So they show that it's possible to use static IDS systems on low edge devices. That's another step. Putting firewalls, yes, but you would only protect the traffic from the network, or you would avoid malicious traffic to go up if they have some kind of rules to do this. So my suggestion here, I think it's something that worth exploring is, okay, why not? Because the attacks now can come from this side. So I can attack the car and compromise the car without passing through this firewall, right?
Sure.
So why not having a distributed IDS system that can use now AI, which this kind of models now, GANs, that they can, networks that can attack each other to improve the model. I don't know if you are
Yes.
familiar with this. I've never used them, but I just know like the concept. So why not putting this kind of networks within our framework to help a distributed IDS system to fight against these attacks or these attacks? And in my opinion, I think this could be a possible solution and lightweight at the same time. Because our framework is lightweight. It can be supported by low edge devices. A distributed IDS can also run. So why not combining both? That was the message that I was trying to pass here. We haven't tried it yet. This is just a possibility. Because I think most of the people was worried about the problems coming from here, but now, as we can see, this is really recent, right? 2022, 2023. But the attacks appear, the breaches are made public, and then you can solve them. I mean, Tesla solved that in a matter of hours or days. But, well, there was a moment that it was possible. If we had this kind of system, maybe we could detect like anomaly in the Bluetooth communication, and maybe the system would react and block. I'm not sure, but this is just a possibility. And it came to my mind, okay, why not combining these two or three fields? But as I said, I'm not an expert, a really expert on this. I'm expert on putting this running on embedded systems. Sandro is more the security guy. He knows about architectures, how to protect physically the device, the CPU, the MCU, but still the attacks can come from anywhere. You have to separate things, right? This is critical, so we put it here. This is not critical, we put it there. This is connected to the network, this is not. This is just connected to the internal network, this is connected to the outside network. So we have to distribute this kind of monitoring and, let's say, the systems that actually act. I think this is something that worth exploring, okay? Yeah, I don't know if it answers your question.
No, it's answers. I mean, it's like because I just asked you a few, and that's nice explanations. I think it's opened up possible explorations for the future. Thank you very much.
Thank you.
Thank you. For the interest of time, we will take one last question. Does anyone have questions?
Okay, thank you very much for sharing these interesting ideas to us. So for this figure, it's very interesting to have like edge training, right?
Yeah.
So, but in our experience, like the distributed model trained by the local data means that it will slow to adapt to the new attack from maybe from another side. Right. So, have you or how you manage, like we have like a distributed model? So how if new attack happen in other side and not in my side? So if I train only with the local data, it will be unknown attack to my model.
Okay, that's
So,
a good question.
Yeah. So have you any idea to manage this model? Because currently, like we try to use like federated learning, but yeah, it's not successfully 100%. It's still the accuracy is not that good that than the centralized model. Also, it's very complicated to have like global and local model, because like everyone, like in the cybersecurity, everyone define their features, their own features, and it means that their model cannot be applied to my site. And I also have defined, there is no standard in the defining the features. Yeah,
That's a good question.
yeah, that's,
I had a slide here, but it's not here anymore
yeah.
because I thought that would be no time for it. But it's a slide that shows how fast the training or how good my training is at the edge that can approximate to the. I mean, you could see the accuracy going from 40% to 80 something, but just in few iterations. It's not here anymore. Anyway, that was a good question. How would I tackle that? Okay, if your model is, okay, you have a distributed model. Maybe you could have an APU, for instance, processor, more powerful hardware for the new training, and then the model will be distributed to the other nodes. That could be an option. Of course, I think it depends on, as you said, if the model is too complex, I cannot put it on an MCU. For the models we use to train the network, which are actually really lightweight models, okay, for the fatigue inference is not, the model is quite simple and lightweight. That's why we try that model with our MCUs. If the model is too complex, of course we cannot use it and train the network. For the model we used, it was really fast to achieve the good algorithms performance. But if we try new models, we have two options. If it doesn't fit, we put in the APU or more powerful hardware. If it fits, I believe it can still have a good performance with our hardware. We just used these two so far. We have to use other models, of course, but so far it works. But I think this is there's no one solution to fit all needs, right? No solution fits all. So we have to adapt. That's what I can think of at the moment. I mean, if you have a complex model, you have to choose the right hardware. But if you have a simple model, you don't have to use a complex hardware. You can offload to this kind of MCU devices. What we have used, it's okay. I mean, even the network is good enough for the model to be shared between the nodes. Thank you.
Thank you.